we can just get Daniel to walk us through the entire Navier-Stokes equation on his own.
Yeah.
He's gonna love it. So here is the first slide that we like to show. See if I can actually make this. Oh yeah, that works okay, right? What's your guys' name?
I'm James.
I'm Clarice.
What's that?
Clarice.
Clarice. This is Daniel. I'm Dr. Goodwin. We'll see if anyone shows up. Maybe they're a little late. Maybe it's rainy. Either way, we're gonna go ahead as regularly scheduled programming. Daniel, what's the top thing say?
So the top one is the conservation of mass.
Correct.
And yeah, that's all you want.
That's the first part, right? That's the conservation of mass. So what do each term mean?
So the first term is how the density changes over time.
Good. And what's that called?
The volume.
The density changing with time is what type of term?
Oh. Well, isobaric comes to term because we talk about that one a lot.
No. This is Trinity's favorite term. It's the steady term.
Oh,
Is the flow
okay.
steady or unsteady? Because if the time derivative is 0, right, then the flow is not changing with time. So this is the steady term. And what's this term?
That one would be we call it the advective term. So that's what changes.
What changes?
The advective.
Yeah, so the advective term changes with the flow.
Mhm.
Flow is brought from one place to another. So what this says then is that the density can only change due to the fact that it's being brought there. There's no sources or sinks, right? Good. What's the second term or the second equation?
So that one okay. It's the conservation of momentum.
Good. Conservation of momentum. Great. And so what does it say?
So that's telling us the first part is the pressure, and that's changing over time. Or changing over like a space.
Good. So if I were to say this in one word, it'd be pressure gradients, right?
Pressure gradient. Yeah. That one is the easiest one, is the body forces.
Mhm.
And that's the pressure, or no, that's the density that something feels due to the force of gravity. And that's why we have the little g there.
Yep. So G, and so if we had electromagnetism, you would add that here as well. This one?
That one, isn't that one connected with the other half too?
They're similar. They both come from the same type of object. That's why they both have mu.
Mhm.
Right? This is the viscosity and the viscosity. Different types of viscosity, but they do different things.
Okay, so I know mu tells us that it's I always think like twisting, so it's like the shear forces.
Mm-hmm.
And that tells us the first one, the one with the two.
Yeah, so this one here and this one here, the I and the J is indicating how the flow in J is changing with respect to I. So that means that you have shearing. So instead of it being in the same direction, which would be compression or expansion, shearing is changes along a different direction. Good. So now you have the viscosity term for shearing and the viscosity term for compression. Good. Cash money. Let's do the next one. Oh shit. I guess I should have made this full screen. You can barely see that, right?
Yeah.
Okay. So what's that top one, Daniel?
So since we already talked about mass and momentum,
Good.
the thing that's left is energy. That's where we see the little E there.
Bingo.
And if you guys, I heard you're gonna retake physics too. I mean, yeah, we've all had to retake it. But we're looking at like when you look at energy, the total energy is the kinetic and the potential.
Yeah.
So that's what we're seeing right there. And we also have the same body forces that we were dealing with, because that's always going to be in life, always going to be pressures.
Good. Okay, so what's this one here?
That's the body forces.
Yeah, so these are body forces, but since this is not a force equation anymore, we would call them. You just said it.
Oh, okay.
Potential energy.
Oh, okay.
Right? So when it's G, right, then you know that that's having to do with gravity, and this is either the work done by gravity, in this case, or in the previous case, it was the force done by gravity.
Mm.
Here we have the internal energy and the kinetic energy. You're just looking at them both together. What's this one out here? This one's the most fun one.
Pressure gradient, right?
Close, that's a Q, not a P.
Oh, okay.
But you're exactly in the right direction. It's a gradient of something.
Well, energy, because that's the Q.
Good, so it's Q. Well, it's specifically not just energy, specific type of energy, we call it heat.
Oh.
So these are heat gradients. And just like you saw in the earlier one, right, they follow the same form
Mhm.
because they do the same thing. In that case, when it was pressure gradients cause motion. So for example, if I have an object like this, and I have an uneven pressure on both sides, it can get it to move. Right, that generates momentum. Here, if I have uneven heating, that can cause internal energy changes. Right?
Yeah.
Okay, now just the four hardest ones.
Okay, and that's them in the bottom, correct?
Yeah, they're sort of separated out. I got rid of the arrows because the arrows help.
Gotcha.
Do you want the arrows?
Uh, no.
Okay, go for it.
Okay, so the one with that has the T in it,
This one?
yeah. So I know the T and the I and J, so that means like a direction.
Mm-hmm.
So that one's the kinetic energy, all of it together, that whole parentheses. So that would be how the pressure changes with space. And the other one is like how. I always confuse the tell a little bit. But yeah, that negative P partial GUJ, that's how
This one or this one?
that one.
Negative P partial UJ. Okay.
Yeah.
Yeah, what's this one?
That whole thing would be the whole the kinetic energy aspect.
These certainly contribute to the kinetic energy, and in fact, we can see them right here.
Mhm.
Right? Oh, wait. Hold on, that's over here. So this one is over here. And it doesn't contribute.
Can you rewrite that though?
Yeah, we do rewrite that. So PDU ends up as PDV. So
That's just the volume of whatever we're dealing with.
this is changes to the volume, right? At a
Exactly.
specific pressure. So this is the PDV work here. And this is the work that we do when we're changing the volume of the fluid. That changes the internal energy, that it doesn't give it the ability to speed up. Over here, this DPDX, that's the pressure gradient term. That's the term that we saw earlier, where I can press something over, right, by having a mismatch balance of pressures. Same form that we saw before, but now it generates kinetic energy instead of generating momentum. Simple? Okay. So what are these two?
So we dealt with how it moves. So that's the internal energy of the system.
This one here or this one here?
The second one. Oh, okay. See, I see how the TIJs move differently. Got it.
Yeah, TIJ is present in both, but it's the question of whether or not you're taking the multiplication of TIJ or you're taking the derivative,
Mhm.
right? So over here, we said that this term generates kinetic energy. So this term must,
Generate potential energy or thermal energy.
no, because otherwise I wouldn't have grouped them. Yeah, they're nicely grouped for you. So this one up here comes down here.
Oh,
This one here comes down here.
so it's like how kinetic energy moves through space.
This one here is, remember, TIJ is the stress tensor. So this is looking for gradients in the stress tensor. How is stress in a fluid distributed? Because if there is no changes in the stress tensor, then you can't generate kinetic energy. What I mean by that is,
The
if we think
friction.
about a box, right? And as I press my hand on the top of a box of water, I can in fact make the water move. Despite the fact that my hand is not in contact with the water at the bottom. The way that I do that is as I move my hand over the water, the velocity is transported down by viscosity. And I can get the entire water block to move over. Right? So this one here is the shearing work. This is the work done by shear in the fluid itself. And then this one here, the last one that we're left with, is called viscous heating. And this is the heating due to this effect, where the oil in your skin that's quite hot, because it's getting rubbed together.
Which one was that again? That was 50?
Viscous heating is here. So
Okay.
it's tau ij is outside and it's du dx. So this term becomes this term. Because this thing here is the definition of the Sij. What do you guys think? You trapped? You ready to go? You're welcome to leave it at any point. I will not take it personally.
This is really relates to like planets, no?
This relates to fluid, yeah, all
Yeah,
fluids. So this is talking about gases, this is talking about liquids. And of course, one thing that we're gonna talk about later in the semester is the interface between liquid and water.
Yeah.
A great example is when we're going to go to the beach next week, we actually see that there is a fluid on top of another fluid. Now you might think to yourself, one of those is a liquid and one of those is a
Yeah.
gas, but they both act like fluids, right?
Yeah, because of the atmosphere, right? It creates a pressure that.
Yeah, the atmosphere has pressure and it also pushes the waves,
Yeah.
right? The reason that you have waves is wind. So they're both fluids in contact with one another. And they all follow these equations.
I'm supposed to be an astronomy right now.
Astronomy, get out of here. Well, as a planetary scientist, I think you should go to your astronomy class too.
Well,
But come
thank
back
you very
in
much.
2.5 years.
I will be back in 2.5 years. And what was your name again?
Dr. Guzmani.
Nice to meet you,
Nice to meet you guys.
Guzmani. We'll be back later.
Okay, bye now.
Bye. Bye.
Okay, so we were talking about vorticity dynamics. Okay, do you remember what vorticity is?
Yeah, it's the curl that the fluid makes. So like
So I say omega is
oh yeah, that it's a cross product
of
of the velocity and the direction. Oh, the curl. It's
the curl. There you go.
Exactly.
You had exactly right. You said the curl of the fluid, and I was like, yes. What about the fluid? You almost had it. Good. So that's perfect, right? So that's the vorticity by definition is the curl of the velocity. Okay. And in particular here, we're thinking about using the vorticity of the fluid because we said that we needed to use simplifications in order to get solutions, right? So let's think about creating vorticity. Okay. So here I want you to think just about this object. Okay, on the left-hand side, you have two densities. And I don't really care if row 1 is bigger than row 2. You can do it however you want. Let's say that the entire fluid is at rest. And there is some boundary that separates them. That's the dotted line that I put in here. Okay. So I want you to think hard, okay, about what happens after I remove the boundary without jostling the fluid at all. Now, this is a miscible fluid. It could mix if it wanted to. That's basically all that I'll say right now. What would happen in a second after? What is the very first thing that would happen? And I want you to draw a box here, on your drawing. Draw a box and show me what you think the fluid's going to look like.
I think that after a second, there wouldn't be much mixing. They would just stay on their own sides. Because because like the only forces that are on it, if nothing's been moved, are just the forces going down of gravity.
Okay.
And maybe if it floats, it has that little floating thing, but it's really just gonna move up and down. So after a second, unless there was that barrier was a solid, and when it was moving it up, you know how we were talking about those like the shear forces, it's touching it, so it's gonna move the fluid. So maybe in the center, there's gonna be some slight mixing. But I think if they're the same densities and all that stuff, they shouldn't move or mix that much or at all after a second.
Okay, I want you to ask yourself a separate question that maybe you can answer here, okay? What is this stable?
No, because it has fluid properties, and if we think about it like a gas, we know that the gas is gonna fill up the whole space. So I would assume that these two liquids would just try to fill up the whole space,
So you keep saying liquids.
or fluid.
Yeah.
I-
So
I-
let's assume that they are
Gases.
gases. What would it look like afterwards?
So yeah, they would definitely, since they're not solid, they're just gonna bounce around everywhere until everything's filled up. So if one was red and one was blue, it would be purple at the end.
It would.
Well, because knowing what I know about gases, they're just gonna go everywhere and hit each other until they fill up the space.
Okay, let's make a clarification.
Okay.
Okay. What happens during, and this is gonna seem non sequitur, but I promise I'm gonna tie it back together. What happens when there's a fire?
Everything goes up.
Or like what are you supposed to do in a fire? Like, let's say there's a fire in your house. What are you supposed to do in order to make yourself safe?
Get down to the ground.
Get down to the ground,
Go outside of the building.
make it to the exit.
Yeah.
Why do you get down to the ground?
As it's hot and everything's gonna rise up to the ceiling, all the smoke and all
Okay,
the.
but I thought you just said that as a gas, they're gonna be mixed.
Yeah. Okay.
So interestingly enough here, right, you're right, that gases love to expand to take up the volume that they can.
Mhm.
But that doesn't mean that they're equally distributed everywhere.
Mhm.
Because to your point, the fact that they rise has to do with the fact that when it's hot, it has lower density. And it's gonna take up as much of the top as it can.
Mhm.
And it's pushing out the more dense air below it.
Yeah.
Right? But that doesn't mean, I mean, you have to keep that fire going in order to fill the entire room with smoke, right?
Mhm.
The first thing that happens is that hot smoke rises to the top. Maybe it's just a little bit, like imagine cigarette smoking, right? That only covers maybe the top of the roof. You'd have to smoke a lot in order to make it all permeate down to the bottom.
Yeah.
Okay. So is this a stable configuration?
I'm only looking at the rows, I'm not thinking about temperatures or anything like that, so if they're the same.
I'm not saying the same. One is larger than the other.
Oh, okay,
One is larger than the other. Maybe let's do two is larger than one.
gotcha. So no, it's not stable,
Why?
because once separated, they are stable, but once the barrier is removed, the denser one is gonna go to the bottom.
Okay, so the denser one wants to slide to the bottom, right? So this one wants to go here.
Mhm.
And what does this one want to do?
That one wants to go to the top. Or it doesn't want to go to the top, it's just being pushed up there.
Oh, it wants to go to the top, right?
Okay.
I mean, the same way, right? Like a buoyant force is a real force, right? So the idea is that the buoyant force represents, if you think about, for example, your hand right now. Your hand is displacing air. And your hand wants to fall straight down. Of course, it's not doing that because you have muscles in your arm.
Mhm.
But there is a slight restoring force from the fact that there are molecules below it holding it up.
Mhm.
Now, there are just as many molecules above it, right? So there's a very little pressure difference here. But if I put my hand in water, then I can certainly feel that there is a force that's holding my body up because it is less dense than I am, right? Water is more dense than I am, 'cause I have all sorts of air bubbles and cavities in here. And of course, if I take my cup, which is mostly empty at this point, and I pop it in water, despite that this is metal, there's air inside.
Yeah.
So the space that it displaces creates a force that really does push it up, right?
Yeah.
So you do feel gravity coming down, but you feel a buoyant force pushing up. Okay, so this guy wants to do that, right? Okay. Well, now look what you've created. Not you, but what we've created. Come on, give me the next slide. Good. Okay, so now we have generated vorticity.
That's it.
What do you?
That's vorticity is just like the fluids going to their like equilibriums.
No. What is vorticity?
Oh, it's the curl.
Good. So you start with no velocity, and then you create velocity. And the direction of the velocity matters, right? Because how is the velocity changing is the point. So if you have velocity that's changing like that, right, you might have vorticity. Okay. So, okay. And let's see next. Okay, let us talk first about vorticity in an inertial frame. Okay, so in order to do this, let's use a vector identity. Okay. What happens if I take the divergence of the vorticity?
Honestly, you get the origin.
What?
I said that you would get the origin of it, but
What does the divergence mean?
you're seeing how it kind of like dissipates over space.
Divergence is an operator, and it's del dot of some function f. You would call this the divergence of f.
And is that on the scalar?
Well, if f is a vector, then it looks like that. If f is a gradient, then it looks like that.
Gotcha. Okay.
Right? So the gradient is without the dot, with the dot is a vector quantity called the divergence. And you're right, conceptually speaking, it's like how is it moving away, right? How is it changing like this, right? And folks online, you can't see my hands, but we're moving them radially, for example. Okay. Do you know what happens when you take the dot product of a cross product?
I know there's one operation where the vectors cancel out and you're just left with the scalar of it, so you're left with like the any animals just like the force.
All right. I want you to do this for me. Use the definition of vorticity and let me know what you get.
And have a gradient square. But
You can absolutely have a gradient square. We have that with the Laplacian.
spread it out. Let me put the square down. So was that a hint, the Laplacian?
No.
No, okay.
There is a very important vector identity here. what is del dotted into del cross let's do
Reminds me of the Q times N times B, or there was a formula like that in ENM. That's similar to that, but I don't.
okay, so this is a vector identity. This is 0.
What, you know what the identity is called? Right.
Del dot del. Del dot del cross is going to be 0. So you can look up this piece here. Just anything with del dot del cross f. Or similarly, if you had something like, if you switch the operations here, you can see that it still works. So del cross del dot f. It's going to work.
Got it. So, okay, no, if, I saw like what you stood for, like if it had the IJ, and we did all that work, then yeah, okay, move 0.
What do you?
No, I understand it's an identity, but I understand that if I would have seen what you like stood for, and like if I did the operation like the 2 gradients, then yeah, I would have canceled that. That's all.
But that would be way more work.
Yeah.
You need to just know this.
Mhm.
Anytime you see del dot del cross.
0.
Right. Similarly, just imagine this as any other function.
Mhm.
Right? Because what does del dot mean?
The dot product.
Right, what does the dot product mean?
The dot product, that's when you're multiplying the 3 different vectors.
Tell me what this means here. What's A cross B?
That's a direction.
Yeah. And how does it compare to A?
Oh, okay, so in the terms of, one tells you the force and the other one tells you how strong that force is gonna be, because it's telling you, one's giving you like the force like X, and the other one's gonna be, okay, it's gonna be like 3X. That's gonna be the full force.
I don't know where you're seeing forces here. This is just.
I'm just using the term force because that's how I know the example from.
Okay, it's just your hand. You just have to do just right hand rule.
Gotcha.
What is this thing?
That is magnet. Magnet. Or don't even use force.
Well, I don't know what you're thinking for. This is just vector identities, right? So it's A cross B.
Mhm.
A cross B. So this is A, this is B, and A cross B is here.
Yeah.
That's it.
Gotcha.
You see?
Mhm.
Now dotted it into A. How can you dot this into this? They're perpendicular to each other.
Oh, so that's 0.
Yes.
Thanks.
This
Cool.
is a vector identity,
Yeah.
right? You have to know this. This has to be part of you.
Okay.
Because del A cross B or del cross U, these are not just things, right? They're directions. This thing has a directionality. And necessarily, right? This has to be perpendicular. Right? Because that's how the cross product works.
Yeah.
Okay, good. Okay, so you can hold on to that idea. I would certainly encourage you to go back and look at your vector calc book.
Yeah.
I know sometimes it's been a while, you gotta dust it off, but in particular, chapter 2 of this book has a good refresher on it. We are gonna do a couple things. Let's assume rho is constant. Okay, so rho is barotropic here, okay? That there is viscosity, but it's not changing with space and time. Let's just assume that there's an equal viscosity in the whole fluid, okay? Then we get to do some really fun stuff. Let me show you some fun stuff we get to do here. Sorry, folks online, maybe I'll just say the equations as we go. Divine chocolate.
Is there anyone on Zoom right now?
Probably not. I know Zori said that she wasn't feeling well, but I suspect some people have just started their. Oh, here it is. Okay. So. The cool thing about vorticity is that it takes advantage of this curl. And physicists try to take advantage of this as much as possible. Because when you're thinking about vector quantities, it gets complicated, it gets annoying. You're gonna have all these terms. If you can set them identically equal to 0 by noting any time that you can do this, you've walked your way out of danger, right? So the first thing to do is to say, let's start with the momentum conservation equation. So starting with equation 439.b, which is written du dt. And I'm gonna go ahead and I'm gonna take the rho and I'm gonna move it over so that it looks like -1 over rho del p, right? That's the gradient. We just saw that at the beginning of class. The rows with the body forces, those are going to cancel. It's going to leave you with just g. That's okay. Right? I'm going to add some of these vector terms in here. Plus, I'm going to use nu. I'm going to use del squared u. Okay? Okay. So that's your momentum equation to start with, assuming those things that we said earlier are fine. And those things that we said earlier are just the following, that the fluid is barotropic and that viscosity does not depend on space or time. Okay. So now let's be clever. Okay. And here's how we're going to be clever. Let's take a cross product of this. Let's take the curl of it. Del cross the entire equation. Okay. So first, let's break apart this one because it has two terms inside of it. What are the two terms inside of it, Daniel?
That would be do we not even, okay, so it would just be 1 over rho gradient p?
No, just these two here.
Oh. Time and
I mean, space. Good. So how do you write this?
that would be. Is it I and J? No. Oh, okay.
Like that?
Yeah. And the partial of u over x.
Yeah, so we can actually, because we're working in vector format, maybe this will be more familiar to you. It's going to look like this. The advective term always looks like this. That's essentially what we've written, right?
Yeah.
Now, by definition, what is del cross u? No, del cross u.
Oh, okay. That one, vorticity.
Good. So let's just rewrite this first term. Del omega del t. Is that okay? Okay. Now we're going to take a cross product of the thing inside.
Is mu in there? Is one of those u's mu?
No.
Oh, okay.
This is just this term.
Gotcha.
Right? The total derivative is the steady and the advective term. We haven't done the right side. That's why the equal sign is still here on the right hand side. Okay. So what about this thing? Del dot or u dot del u, but now I need to cross it. So let's do that. Del of u dot del u. This is another vector identity. I'm gonna go ahead and guess that you haven't memorized it. That's perfectly okay. But this would be in the back of the book, or this would be in the vector calc book. I will tell you this one is not one that I have memorized recently. So I'm gonna read it out of the book. Okay. Basically, what we can do here, u dot del u, we can take this and we can turn it into this piece here. We can turn this piece into del of u dot u over 2 plus del cross u cross u. And of course, this thing is omega. Now, if you can't immediately see that, that's perfectly all right. I don't think anyone looks at that and thinks that. But because we have this relationship in the vorticity of del cross u is something else, we want to take advantage of that as much as possible. Because look what I tried to do here. I'm already taking the del cross. Now it's just this piece here, right? So if I can trick the equations into giving me del cross del dot anything, I'm good, right? Because we just figured out why that would be. So now look what I've done. I've taken this vector identity, which splits it up into del of u dot u, right? So this piece here, once I take the curl of it, it's gone. And then I just have this thing of this thing. Now that's a nightmare, don't get me wrong, right? But it's better than this thing here, del dot del times u. Okay.
So that identity is a lot of algebra.
This one here? Yeah, so this one looks like, I forget exactly what it is. It's something like a dot del b, and it's del a b over 2 plus del cross a cross b. Let's see if maybe these are in the back of the book. Oh yeah. Yeah, so if you look at B313 in the appendix, it has, well, it has del cross U, but you can get it from, let's see, which one did we want to use here? U dot del. You would have to rearrange some of these versions, but it's in here. Yeah, I would recommend B3, B.3 in the appendix has a lot of really helpful identities for doing this type of math.
We're mostly gonna be dealing with spherical.
No, but just at the very beginning there, it talks about vector identities, right? And you want to kind of think about how we can use them, because those vector identities, when you see them, right, it's one of those things where it's a shortcut, right? As soon as you see it pop up in your work, you're like, oh shit, I can make that into something more manageable.
Yeah, kind of like
No,
doing all the, I was doing all the integration in the homework.
Yeah, and the same thing is true, right? So like, as you get more comfortable knowing these vector identities, you can also use them as a target. So what I mean by that is it is completely valid to look at a group of equations or a system of equations and to recognize, wait a second, if I take the curl of this thing, or if I take the gradient of this thing, then I know it must be equal to something that I can actually manage, right? So similarly, the reason that we started on this at all is because we created this thing, which is the curl of something. And so now people who love vectors, they say, wait a second, if we can find an opportunity to take the divergence of that, then it'll disappear. Right? So terms that are the divergence of the curl, they're going to be gonzo. Okay. Okay, So I can just rewrite this piece now. This whole thing is gonna be d omega dt. And this term here is 0. So this is just del cross u, oh, sorry, del cross omega cross u. Okay. Excuse me. Now here's a question. What is the curl of this thing?
I don't think there would be one, because wouldn't it be? Well, it depends on the scenario, but wouldn't it be constant?
Not constant, right? That's not pressure, that's pressure.
The.
There you go. That's really important. Okay, it's not just pressure. It's the pressure gradients.
Pressure everywhere. That's what.
Well, there is pressure everywhere. We already know that, right? What this is saying is this is the momentum generation due to pressure gradients, unevenness in the pressure, right? And we have an expectation that the pressure should be uneven. That's what gives rise to momentum. Okay, but this is del dot P. What is del cross del P? Go back to our B3. B311. B.3.11.
I was thinking it'd be something like. Number 13 or something.
What is B.3.11 say?
It's that the gradient, cross product of the gradients of rho is equal to 0.
Good. Does it mean rho there? Do we actually mean the word rho?
No, I think that's just a simple use.
Yeah, so it's a scalar symbol, right? The only difference that they have here in the books is talking about the difference in vectors and scalars. So U is their example of a vector and rho is their example of a scalar. Is P a vector or a scalar?
It's a scalar.
Good. So it must be B.3.11, right? So in that particular circumstance, this is saying that if I take the curl of the divergence of a scalar, or sorry, of the gradient of a scalar, it is always 0.
Can you repeat that again?
Yeah.
You take
If
the.
I take the curl of the gradient of a scalar, it is
0.
always 0. Just like we showed, right? That the divergence of the curl of a vector is always 0. And in fact, if you look at B312, what does that say?
Gradient dot product of a vector cross product. Yeah.
Right? Like, I mean, it's perfect. So if we know these vector identities like the back of our heart, then we see this and we say, hey, if I take the curl of the divergence, of the gradient of P, then it's gone. Like goddamn chalk. I need like a chalk like wrist holder, you know? Oh, here it is. Okay. So this term's gone. Okay. What about G?
That it also be gone?
Yeah, why?
Because I'm thinking about how gravity and pressure serve like different, like similar roles. Because
Okay.
they're both kind of like scalars act. They're both acting on us constantly. And Yeah, that's kind of.
That's not exactly how I would say it. You're on the right track, but you're missing a little bit of the language.
It's constant.
It's not.
Gravity is.
Neither is pressure. Pressure is certainly not constant.
Okay.
This is what we call a scalar field. It can vary, like for example, take this room. There's different pressures all over the room, right? And certainly gravity can vary. It can change as a function of height, right?
Oh, okay.
Okay. But the thing they have in common, this term is del P, the gradient of P. How can I write G? Let's remember that I can write this as del phi, where this is some vector potential, right? Or sorry, this is some scalar potential. And then I just take the gradient of it and I get this, the force, right?
So you just same thing as that again.
So as long as G is conservative, right? As long as the body forces are conservative, then this one's gone. Right? And this is the power of the vorticity. Now all I have is del cross nu del squared u. Okay. Can I do anything with that?
Well, is there a way that you could expand the center, parentheses one?
Oh yeah. So we'll get to that in a second. What about this one?
Yeah, that mu gradient to or delta to u.
That's not this one, right?
No,
So they're not the same.
Yeah.
How can I rewrite this?
say that we're just gonna give a whole new symbol to that, won't be bad. But
No, you're gonna use an old symbol.
but those three become just one symbol. Just so we could get the gradient across whatever format again.
I don't want a gradient cross in there.
Gotcha. Okay, so you're trying to get rid of that. Mhm.
Let me ask a separate question. Del cross del squared of A equal to
Oh, that would do that.
That's my question. Can I do this? Is this valid?
No, I wanna say no, unless like they share like those like reciprocal identities and you would do like an algebra with like dividing and multiplication, different.
No, this is very much okay.
Yeah.
So it's not clear why it's okay. Let me show you why. Del squared A, right, is a vector operator that gives you a vector in the same direction as A. The directionality comes from A.
Okay.
And del cross A, still the same direction, right? Because even if you think about it in terms of del cross A, right, this thing is still in the direction of A. So your del cross A is still in the same direction,
Okay.
right? This one's fine. So this is del cross A being done beforehand, and then the del squared operator. So this becomes what?
Do we leave mu inside?
Well, I can do this, right?
Okay. And then it's gonna be parentheses that del cross, or yeah, del cross u,
Which is?
which would be the vorticity again.
So look at what you've done, right?
Mhm.
You started with this thing, a nightmare, super hard. 1, 2, 3, 4, 5 terms. And what have you gotten it down to? 1, 2, 3 terms. You got rid of 2 terms. You got rid of the gravity and you got rid of the pressure. And we said they're all gonna just matter based on how we distribute the vorticity. Okay, so let's clean this one up a little bit. Okay, I'm gonna start again.
Wait, so that's the whole, the initial the reference inertial, reference point, that's what. This was whole, that's what you're showing, right? That depending how you look at it, you can cancel out some of the symbols.
You mean taking advantage of this?
Yeah.
Yeah. Well, that's what we did, right? We took advantage. Now you have to be very careful, right? You have to do the vector identities properly. You have to look for stuff that disappears, right? Okay. So let's rewrite this guy, because he's a nightmare. How do I rewrite this guy?
You have like a vorticity squared.
What?
Well, okay, well, it would be. Well, vorticity cross vorticity, because can you group up that gradient and that cross U to get another vorticity?
Why don't we use the vector identity?
Okay,
Okay, which vector identity do you want to use? You have the book there?
yeah.
Okay, which vector identity do you want to use there? Yeah. Because you're right,
313.
What?
Last one, that looks closest to that. Except there's no parentheses.
Well, we want to get rid of having a triple cross product or a double cross product is sucky, right? No one loves that. Is there a way to rewrite this maybe in terms of like dot products or stuff that's easier? Because if I can get something that's like u dot or del dot u, right? You can take advantage of the fact that that term would be 0. No?
Yeah. So it would be, the gradient parentheses W dot U.
Gradient, what?
The upside down triangle, parentheses, vorticity dot U. I'm looking at the first part of 3.9.
Okay, I think you should look at b.3.10.
Oh.
Where it says u dot del applied to omega minus omega dot del applied to u. Right? Okay. Some other terms can fall out because you have u dots that are going to disappear. But have a look at what I just wrote. See this? U dot del u. U dot del u. U dot del. Oh, look at that. These two terms together are shit, let's go, boy. Okay, so let's move this to the other side. Okay. That's omega dot del U plus del, or sorry, nu del squared omega. This is the power of vorticity dynamics.
Wait, that's the power of vorticity dynamics.
So we have taken the Navier-Stokes equation and we've made it solvable. Okay, now you don't see it yet, but I'm going to show you. Okay. On the left-hand side, just like we had earlier, that the generation of momentum is due to some sources or sinks. We now have a statement about the generation or the creation or subtraction of vorticity itself, spinny upness of the fluid. And notice, I don't give a shit about the pressure. Pressure is always giving me a hard time, right? Because in order to know the pressure, you got to know the density everywhere. You got to know the temperature, right? We're saying, let's ignore that. Similarly, I also don't care about the gravity, right? Because this is a connected fluid. I cannot get fluid to move from one place to another without also having that fluid move with it. Vorticity lines, they permeate the whole fluid. Vorticity tubes and vorticity like structures within the fluid, they turn and they contract and they twist as the vorticity lines get closer, then the fluid is spinning up faster as they separate, and the fluid is spinning less. That's telling you a lot about the movement of the fluid, right? Okay, so that's what this says. How do I generate vorticity? Well, I can do it in two ways. This one is the easiest to understand. Del squared of the vorticity, the del squared operator, just like we saw with the del squared operator when it comes to fluid velocity, this is diffusion. So let's say you start with a really tightly packed bundle of vortex lines. In some vortex tube, that's very tightly packed. And you just wait. They're just going to slowly diffuse out of the tube. Right? That's the process of diffusion in the fluid.
So in the example of, you know how you used to get like those two soda things and spin it up?
Yep.
That, what you're mentioning there is as it goes towards or just as the spinning stops. Okay.
Diffusion usually takes longer than that.
Okay.
When you've got the two tubes and you're moving them, that's really kinetic in nature.
Okay.
And the question we always have to ask is how long is the diffusion time scale?
Hmm.
So if, for example, take a toilet bowl and you drop a little bit of like toilet cleaner in it, the blue stuff, right? Maybe right after you flushed it. So it's already spinning, right? And you drop it in there. How well does that fluid then move? Like, does it make the whole bowl thing, or does it? You have to wait for it to come to a stop before it makes the whole thing, right?
Gotcha. And that's what you're talking about, that it's all being carried. Right. Got it.
Yeah. So this part here is just the diffusion of vorticity in or out of a region. Okay, so you can diffuse it. Now this one's a little weird, and this one you maybe don't have an intuitive sense of, but this is essentially saying, how does the vorticity travel with the fluid? Or more specifically, how do stretching and tilting of vortex lines generate vorticity? So what I mean by that is omega dot del is looking at how much of the vorticity is dotted into changes in U. So if, for example, I tilt my vorticity line, I can generate vorticity from the tilt.
Okay.
You'll see this in practice.
Gotcha.
Yeah, this one is very unintuitive. By the time that we've gotten here, we've taken an abstract concept like the curl, and now we're trying to understand.
Is that similar to, you know, that example with the ball? Cause like it's spinning, so it creates a different pressure in one area, so that's how it's generating lift from itself or something?
We don't have pressure.
Oh,
We don't think about pressure anymore. When we're
Yeah.
talking about vorticity, pressure doesn't exist,
gotcha, okay.
right? Because we made this assumption in order to make the equation softer.
Hmm.
All we're thinking about now is we're thinking about this concept of the spinniness of the fluid. And the ways to generate spinniness is to either let the tubes diffuse or to tilt them. Okay.
Better not be trying to swear.
All right. So let's show it. Okay. It kind of works. It's cutting off a little bit. What's this gonna look like? This is called the driven cavity test. And this is basically, there's when we do computational fluid dynamics, we use test cases to determine whether or not your code is working. This is a classic example of whether or not your vorticity code is working, right? So what you can do here is the picture is 3 walls, stationary walls, object initially at rest, and then you start moving the top wall. Okay, inside, you don't even have to specify anything. Right? You don't have to specify that the fluid has gravity. You don't have to specify that the fluid has pressure. We assume that the density is constant. We assume that there is viscosity, but that it is uniform, right? And then the question is, what does the fluid look like 20, 30 minutes into the simulation? You know, you start it from rest, you start it from doing nothing. What does it look like after it comes to steady state? Because I put in here this picture, right? My expectation is that it's moving to the right, does this.
Yeah.
It's not right. Or do I get tons of little circles up here and then nothing down here? Or do I get, you know, this moves down and then it moves across the wall and it goes back up and it creates a counter current at the bottom?
Yeah.
Right? So this is a test for your solver. Can you create a simulation of something that just simulates the vorticity? Okay.
So
What?
how should the fluid move in this scenario?
Let's just find out, right? You're gonna do it.
6.8.
I believe so. Let's just check. 6.8 is still linear affection. It must be in the next homework. Yeah, 6.10.
I was seeing there was some code, but there was only in 2D. It's gonna be in 2D, right?
For which one?
This one you're talking about.
This is 2D, yeah, it has to be 2D, right? Yeah, this is solved on page 253. They solved the driven cavity vorticity stream function. And I think they give you a picture. But I think it'll be up to you to determine what it means. Okay, questions, comments, concerns?
No, but this kind of like one-on-one.
I mean, I don't think so, but
Gotcha.
unless you want it to count as your one-on-one. Hi, Zori. Sorry you couldn't see anything.
Hi, it's okay.
We basically just did, let's see which part of the book this was. This was just equations 512 to 513.
Okay.
And a lot of vector identities on the board. Maybe Daniel will be kind enough to take a photo and send it to you.
Yeah.
Because I'll just
Okay.
try not to delete it right now.
Okay.
Normally I think I would go a little bit longer, but considering this is all you need to do the stream function and then it's spring break, just give people let them fuck off if they want.
Okay, sounds good.
Okay. Any questions, Ari?
No, sounds good.
Okay, thanks for coming.
Thank you.
Bye,
Bye.
y'all.